Alright, let's go ahead and continue solving systems of equations by substitution. We're going to do example number 2 in this video, the no solution option. And if you recall from doing systems of equations with graphing, the only time we end up with no solution is when we have parallel lines. And that's because in order to solve a system of equations by any method, graphing or algebraically, a solution to a system is in fact a single coordinate point. That coordinate point exists on either line. In fact, it exists on both lines when the two lines have nothing to do with each other. So when you graph them or solve them at the same time, that single point exists on both lines. So the solution to a system is actually a shared or a common point between any two lines. We're going to go ahead and flip it straight to example number 2. I'm going to show you just the left-hand side to start with. Example number 2, we have an equation in standard form there, 4x minus 3y is equal to 15, and y is equal to 4/3 x minus 7. Just like we did in the last problem, when we are substituting something, that means if y is equal to 4/3 x minus 7, we're saying they're the same thing. Y is that entire quantity there. You can substitute one for the other. They're equivalent. They are identical. So anywhere we see y, we could put 4/3 x minus 7 in instead. So we're just going ahead and put that full value inside the other equation. I'm going to rewrite our top equation, 4x minus 3y is equal to 15. But instead of y, we're going to say 4x. We're going to say 4x minus 3 times y's equivalent, 4/3 x minus 7. That's all equal to 15. Don't forget to write the right-hand side of your equation in. Now, when we get to a fraction and a whole number, a lot of you guys still struggle, or not even struggle, you just don't really like working with fractions. So I wanted to remind you of this trick up here. If I were to ask you what half of 2 was, what would most of you guys say? What's half of 2? I'm sure everyone's thinking 1 at this point, right? When you have a number on the outside and the denominator is the same as the number on the outside, they cancel and we get to preserve just the numerator, just the top. Half of 2 is in fact 1, which means negative 3 times 4/3. When you go to distribute that negative 3, these 3's will cancel. The only thing you need to be really cautious of is you have to keep the sign. That's a negative, that's a positive. When you multiply them together, they're going to become negative. So then you preserve the numerator and the variable that's attached to it. So we're going to start here. That first 4x we did not use, so we're going to bring it down. Negative 3 times 4/3, those 3's cancel out, and I keep the negative here, the 4 in the numerator, and the x next to it. So that is not being very friendly. And then we also have to multiply that negative 3 times the negative 7 there. When you're dealing with numbers on the outside, you do attach the operation to it. Negative 3 times negative 7 is positive 21. And then the right side equals 15. Our next step here would be to combine like terms. Any integers or variables that are on the same side and the same term, you have to combine them or collect them all together. Our integers are safe for now because both of them are on opposite sides of the equal sign. But here on the left, you can see that we have x twice. I have 4x minus 4x. That actually becomes 0. And all I'm left with is 21 is equal to 15. Now, all of you guys should have taken pause there. 21 does not equal 15. That's not even possible. And the reason that that's not possible, or the reason we come to that solution and we don't just come to a term like this one here where we solved for a variable and it was exactly one number, is because the solution to a system is a shared point, a point that exists on both this line and this line. These two lines are parallel. They don't share a point. They never intersect. So I'm not actually expecting them to intersect, but what that does is it creates a false statement. It creates a statement that we know can't be true. So in effect, because that statement can't be true, because we created a false statement, it verifies that there is no shared point or common solution between these two equations. This system has no solution. Go ahead and pause the video here if you need to take down any notes, and then we will move on to example 3. All right, so the very last example we have is many solutions. You can actually also call this infinite solutions if you wanted to take note there. Sometimes in other textbooks or resources, you'll see the example infinite solutions. When you look at these two equations, at first look, they don't necessarily look like the exact same equation, but that's actually what's happening. This is slope-intercept form, and this is standard form. If you were to rewrite this equation into slope-intercept form, you'd end up with identical equations. But I'm going to show you what happens when you just use the traditional substitution method to solve for this. Once again, we have a y equals statement, so y is the equivalent. It is the exact same thing as that quantity there, and we're going to plug it into y in the bottom equation, or the second equation. If x plus 2y is equal to 8, then x plus 2 times what y's equivalent is also has to be true. And then I'm going to make sure I write equals 8 so I get both sides of the equations captured there. Just a second to focus this for you guys. Come on. All right, there we go. So all I did is instead of writing y, I wrote what y was equal to. You have to make sure you're careful every single time. You're not writing y at any point. So actually, if you look here, all you're left with is x's and numbers. And that's because when you substitute a value, you replace it. We replaced y with its equivalent. So now we are going to bring this x downstairs because we haven't used it at all. And we're going to distribute that 2 that's on the outside of the parentheses across both terms. We have a situation again here where the denominator cancels out with the outside number, but now we have a positive number. So we're going to cancel these 2's here. We're going to save that negative 1 in the numerator and the x that's attached to it. So I end up with negative 1x there. And then 2 times 4 is 8. So plus 8, and that all equals 8. All right, we have x minus 1x. Well, that cancels out and becomes 0. So all I'm actually left with is 8 equals 8. That's true. We all agree that 8 equals 8, correct? So unlike the first one, we actually did not produce a statement that showed that a variable was equal to a specific number. And better than the second one, we didn't create a false statement, we created a true statement. But why exactly would that happen? Why would we eliminate both x and y and only create a true statement of an expression, essentially, of 8 is the equivalent or equal to 8? That's because these two equations are also equivalents. They're identical to each other. So we would expect every single solution they could possibly produce to also be identical to each other. That is the whole premise of a system of equations that has infinite solutions. If every single point on a line is a solution to just one line, then we would expect every single point that is in a system to also be a solution to both equations if the solution is an infinite solutions system. So because the lines are equal, we would expect every solution to also be equal to a point on both lines. When we create a true statement, when we create a true statement and there are no variables involved, we know There are many or infinite solutions. All right, that is it. Let's go ahead and get this in a frame you can see it. Go ahead and pause the video here and take down anything you didn't get. And we are done with solving systems and substitution.